Okay, I might get started. Welcome to today's ARC Center of Excellence for Enabling Eco-Efficient Beneficiation of Minerals signature lecture by Professor Jun Oshitani from Okayama University of Science. I'd like to start by acknowledging the traditional custodians of country throughout Australia and their connection to land, sea, and community. And we pay our respects to their elders, past, present, and emerging, and extend that respect to all Aboriginal and Torres Strait Islanders peoples today. And so I'm very happy that Jun is able to join us today. Jun is my good friend and colleague for almost 20 years. We met, I think, in 2005, and we've had many good collaborations. And I've visited Japan many times, and Jun has spent several visits in Australia. And we're hoping to arrange that he comes here next year in April to spend some time in April. And so with that, I'll let him tell you about his work on dry separation based on float sink and density segregation in gas solid fluidized beds. Thank you.
All right, may I start? Okay. Thank you, George, for giving me a good opportunity to talk today. Good morning, everyone. I'm Jun Oshitani. It's very hot and wet in Japan right now. Okay, today I'll talk about dry separation based on float sink and density segregation in a gas solid fluidized bed. First of all, let me talk about float sink. In the picture, a wood chip and the stone are just on the sand, but the sand is fluidized when the air floats to the bottom. This is a gas solid fluidized bed, and it looks like a boiling water, so a wood chip floats and the stone sinks. The float sink can be applied to dry separation instead of conventional wet separations, which have various disadvantages. We designed and made some lab-scale dry separators with my partner company, and we commercialized the dry separators for waste treatment like waste plastics and waste non-ferrous mixed metals. This is a huge separator for waste plastics. Let me show you a movie of semi-automatic separators for non-ferrous mixed metals. To separate aluminum and copper zinc, they use black powder like this. What do you think this is? This is iron powder to make higher separation density. The floated aluminum is recovered by hand, like a cooking chef. So this separator is relatively cheap. This is the floated aluminum. For the sunk copper and zinc, a cage, a basket, is pre-installed at the bottom, and automatically lifted up, and the slider is moved by hand, and the bottom mesh plate is opened to recover the sunk materials. These are reused as materials. Nagata Engineering is the partner company. And we also applied the dry separation to mineral processing with George. We have collaboration since 2008. Actually, we met 2005 in Terrigal, you know. Anyway, we're good friends for a long time. I visited Melbourne with my family, and George visited my city, Okayama, and we love karaoke. We published papers since 2010 about lamp iron ore, fundamental studies, and coal, and continuous separation, and particulate iron ore using the density segregation, and copper ore. Number 10, economic water and energy variation of early rejection of GAN from copper ore. This is very nice. And recently, we focus on vibrated fluidized bed for density segregation. I'll talk about it later. This is a lab scale dry separator for the mineral processing. We got lump of mine, lump iron ore from Australian big company and carried out the separation. This movie was made by partner company Nagata. This is a feed of iron ore. Here we use the mixture of the silica sand and zircon sand to adjust the separation density. The floated stones are recovered by the rotating basket. And the sunk heavy stones are recovered by a small cage. The cage moved at the bottom and partially moved at the wall. And there are some powders attached to the stones, so they are removed by the trommel. And these are the discharge of the separated ones. We carried out the chemical analysis, and we found the separation efficiency is almost same as that of the conventional wet separation. We also carried out using lump coal. These are floating combustible coal and recovered by rotating basket. And sinking silica stones are also recovered by the small basket and treated by trommel. These are the floaters and sinkers, separated enough. All right, from now, let me talk about our fundamental research entitled Float Sink of Large Objects in a gas or fluidized bed different from that in a liquid. The float sink in the fluidized bed looks like that in the water. So we had a question. Is this based on Archimedes' principle? Our answer is mostly yes, but sometimes looks no. So today, let me show you three interesting phenomena. The first is anomalous sphere sinking at the air velocity just below UMF. The UMF is minimum fluidization air velocity. So when the air velocity is above the UMF, as I shown, the float sink occurs. Of course, it does not occur at a fixed bed. Here, it looks like a fixed bed, but float sink occurs. Air velocity is just below the UMF. So it is like apparently fixed bed. Very interesting. So we carried out more experiments to know the details. Glass beads were put into the container. The air was put through the bottom as U by UMF is 0.95, just below the UMF. Various density spheres are prepared. The density ratio was like this range. The sphere was put onto the bed surface like this. Video cameras are prepared. Then the sphere sinking was recorded like this. And the time dependence was analyzed. 0 floating and 10 sinking. This is the result. Light sphere gray floats and the heavy sphere purple sinks. Blue and green. The depth becomes smaller with decreasing the sphere density. So red has to be between green and green and gray, but finally between green and blue. So surprisingly, a lighter sphere red sinks deeper than the heavier sphere green. We also carried out the experiments in the yellow region, light gray, and heavy green. Light orange deeper, light pink deeper, and lighter red also deeper. This is a final depth as a function of the density ratio. The final depth increases with sphere density. This is natural, but in the yellow region, lighter spheres sink deeper than heavier spheres. An interesting point is this occurs at the density ratio is about 1.0. That means the sphere density is close to bed density. What happens? These are pictures at the bed surface with spheres. In case of lighter sphere left side with bubble, and in case of heavier spheres right hand without bubbles. These are the movies. Heavier spheres sink without bubble. But in case of lighter spheres, there are bubbles around spheres. So this is local fluidization. The sphere is gradually sinking inside and bubbles are still generated, as you see. Then we have a question, why with or without bubbles for lighter or heavier? Let me talk about the possible mechanism. This is the powder bed. Particle contact force is larger at the lower layers, but the force is weakened by an air through the bottom. In case of lighter sphere, the particle contact force is not changed. The air comes outside at the bottom and joined together. So here, the air velocity is larger than UMF. Then bubbles are generated locally. In case of heavier sphere, the particle contact force below the sphere is enlarged due to heavy weight. So the air goes up far from the bottom And there is no local increase of air velocity, so bubbles are not generated. We have another question. Why the sinking depth is dependent on sphere density? Void is formed below the lighter spheres. Here we have the local fluidization. In case of much lighter sphere, just floating with bubbles. But in case of density ratio around 1.0, due to the void, bed density below the sphere becomes smaller than sphere density. So the sphere gradually sinks with bubbles generation. But the particle contact force is large at lower layers. So finally, the bubbles generation and sphere sinking stop. In case of heavier ones, the sphere sinks slightly without bubbles or sinks deeply by overcoming the particle contact force. The second is unstable sphere sinking at higher air velocity. Here, various density spheres were prepared, and glass beads were fluidized at U by UMF from 1.5 to 7.0, higher air velocity. After 3 minutes of the float sink, the normalized height of sphere was calculated like this. These are the results. Normalized height as a function of the air velocity ratio. If the sphere density is small, like 0.8 and 9, the spheres float at all air velocities. And if the sphere density is large, like 1.4 or 5, the spheres sink regardless of the air velocity. But if the sphere density is middle, like 1.0 or 1.1, the sphere float at lower air velocity but tend to sink as increasing air velocity. Because if the air velocity is increased, the bed expansion occurs. So the fluidized bed volume becomes larger and the fluidized bed density becomes smaller. As the result, the spheres tend to sink as increasing air velocity. So we expected the spheres sink at much higher air velocities. However, as you see, spheres float. These are for density equal 1.2 and 1.3. Again, the spheres float at higher air velocity. So the sphere sinking is unstable at higher air velocity. As a possible mechanism, my colleague Tak, he is an expert in numerical simulation of the fluidized bed. He says there are 3 forces working on the sphere in fluidized bed: particle contact force, fluid force, and gravity force. The fluid force is important, especially the gas pressure gradient force is important. In gas flow through the dense particles bed, large pressure gradient due to particles, background pressure drop exists like this. His model is designed to capture the pressure gradient due to particle around sphere. So this is similar to Archimedes' buoyant force. These are his numerical simulation results at the air velocity ratio 1.5. Isobars are evenly spaced like in the water, so the float sink looks based on Archimedes' principle. These are at 6.0 higher air velocity. As you see, the isobars are not evenly spaced due to local uniformity. So the float sink looks not based on Archimedes' principle. The local uniformity is big difference with water. The third is many body effect on floating sinking in a fluidized bed. This is most recent result. So George, it's a first for you too. Okay. In the previous experiments, only one sphere was put onto the bed surface, but here the number of the sphere was changed from 1 to 10. The air velocity was fixed at 1.5 F, and after 3 minutes of the float sink, the normalized height of the spheres were calculated. This is the average normalized height as a function of number of sphere. In case of lighter sphere, the spheres always float. In case of heavier one, the sphere always sink, but between them at 1.3, the sphere floats where the number is 1 or 2, but the sphere almost sink at larger number. This is completely different from the float sink in the water. The experiments were repeated from 3 to 7 times at each number. These are our results. The spheres mostly float or almost sink, not scatter in the fluidized bed. The experiments were repeated from 3 to 7. These are the movies. In case of 1, the sphere is always floating, but in case of 5 and 10, some spheres are sinking. This might be a kind of many body effect. Float sink in the fluidized bed still, we believe the float sink in the fluidized bed still hide the mysterious phenomena, so we'd like to enjoy them. All right, let me change the slides. So just a moment. All right, next topic is density segregation in a fluidized and or vibrated powder bed. As I shown, we got good results with the float sink separation, but unfortunately, this has a weak point. Smaller mixture like less than 10 millimeter cannot be separated because such smaller stuff is strongly affected by fluidized particle movement, so the float sink is unstable. Then we also developed the right separation based on density segregation. The left picture is a mixture of glass powder and iron powder. If the density difference is large enough, the mixture can be easily separated. So we applied this dry separation. We applied this to dry mineral processing to upgrade particulate iron ore and coal. But this dry separation also has a weak point. If the density is small or side range is large, unfortunately, the mixture cannot be separated. Then we added particle vibration to the fluidized bed to enhance the density separation. For example, this is the separation of wet chips and the gravel in construction waste residues. The mixture is well fluidized with the vibration. The left side. And the separation of waste from lapis lazuli blue gemstone processing. This is a joint research with Japanese style artist. The blue powder is used as natural mineral pigments. He is the artist, and he is also a professor of art university. The blue tiles in the background were drawn by children with the lapis lazuli powder. I'm enjoying the joint research as well. All right, from now, I'll talk about the separation of a fine particular sand mixture using vibrated fluidized bed. This is research of Mr. Subo. We got a typical lump of mine particulate sand from Australian mineral company, the mixture of heavy sand and silica sand. At the mining area, wet spiral separation like the left side picture is used to separate the sand mixture, but there are various disadvantages. So we tried the dry separation using vibrated fluidized bed. The sand mixture of this side range was prepared and used. This is a vibrated fluidized bed. It has a cylindrical column in a diameter 100 millimeter. Airflow is put from the bottom, and the superficial air velocity U was varied by an airflow controller. There are two vibration motors to generate the vertical vibration. The amplitude A was varied by tuning unbalanced weights in the vibration motors. The frequency F was controlled by inverter. Vibration intensity gamma, the ratio of vibration acceleration and the gravitational acceleration was calculated like this, using the amplitude A and the frequency F. The sand mixture was put into the column to be these heights and fluidized and vibrated. After 60 minutes, 12 layers of the particles were recovered, and the bulk density was calculated with the weight and the bulk volume. The experiments were carried out of the three cases without or with vibration at 120 or 240 in height by changing the velocity ratio and vibration intensity. At first, the effect of air velocity ratio on the density segregation. These are bulk density at each layer given without vibration. I mean only fluidization at various air velocity ratios. As you see, the density is almost same regardless of the air velocity ratio and the layer number. That means the density segregation is not induced by only fluidization because the density difference is too small. These are with vibration. When the air velocity ratio is 1, upper layers density is around 1.4 and lower layers density is around 2.4. So the density segregation clearly occurs by adding vertical vibration to the fluidized bed. These are the movie. The left one is without vibration and the right one is with vibration. As you see, the dry segregation clearly occurs with vibration. These are pictures of the 12 layers. The upper layers are silica sand and lower layers are heavy sand. So the sand mixture was separated by the vibrated fluidized bed. Again, these are the results at 120 in height, and these are at 240. We got similar results. The clear density segregation occurs at the dense air velocity ratio 1.0. These are the density at each layer as a function of the air velocity ratio. The density at upper layers decreases and returns to the initial value, and the density at the lower layers increases and returns to the initial values. The similar results are obtained at 240 in height. Based on this data, we calculated segregation efficiency, degree of the density segregation, using this equation. This is the segregation efficiency as a function of the air velocity ratio. Again, no segregation without vibration, but segregation occurs with vibration. And the interesting point is the minimum fluidization air velocity UMF produces the maximum density segregation in the vibrated fluidized bed. Next is the effect of vibration intensity on the density segregation. The experiments were carried out at the air velocity ratio 1.0. With increasing the vibration intensity, density segregation occurs and disappears, and again occurs and disappears. At 240, the density segregation occurs and almost disappears, and again occurs and disappears, surprisingly. So the segregation efficiency goes up, down, and up, down, and slightly up. At the bed height 240, the same way going up, down are repeated. But the peak points shift to the right side at 240. So possibly, this is a kind of resonance phenomena. Degree of the density segregation is resonant with the vibration intensity gamma, and the resonance frequency is dependent on the bed height. In general, the effect of vibration is discussed with the vibration intensity gamma, but it contains two parameters, amplitude and frequency. So we are interested in showing the result with the two parameters. At the bed height 120, for frequency, the data plots are scattered, but there's only one large peak at amplitude around 0.4 millimeter. So here, segregation efficiency seems to be correlated to amplitude. On the other hand, at 240, for amplitude, the data plots are scattered, but there's only one large peak at frequency around 22 Hertz. So here, the segregation efficiency seems to be correlated to frequency. So phenomenon is very complicated. Unfortunately, we don't know why at the moment. We also studied the dependence of density segregation on air velocity and vibration intensity. At first, conversion from reverse segregation to normal segregation. Do you know Brazil nut effect? It happens when granular mixture subjected to shaking result in bigger particles ending up on top. This comes from size difference. In case of powder mixture of a same size, different density, it is well known that reverse segregation occurs with vibration only. Larger density particles go up and the smaller density particles go down. But in case of vibration with airflow, as I shown, normal density segregation occurs. Then we simply had a question: at which air velocity does reverse segregation convert to normal segregation? So we did experiments. We prepared 2 mixtures of glass beads and stainless steel powder or iron powder of same size but different density. The mixture of 50% bulk volume fraction. The vibrated fluidized bed is same as the previous topic. The vibration intensity was 4.4 or 3.4. We followed a similar procedure for the experiments. After 10 minutes, 10 layers were recovered and the bulk density was calculated with the weight and volume. And then volume fraction of heavier particles was estimated with the bulk density. This is the result of mixture A. Only vibration or at smaller air velocity, upper layers contain heavier particles, so reverse segregation occurs. If the air velocity increased, lower layers contain heavier particles, so normal segregation occurs. And at larger air velocity, the particles are mixing. These are the movies. Oh, it doesn't work, just a moment. Oh, perfect. It's not easy to see, but light colored glass beads, just a moment. Here, move to lower parts at only vibration and smaller air velocity, you see? So reverse segregation occurs. These are the results of mixture B. Same as a mixture A, reverse segregation occurs at only vibration or smaller air velocities. And with increasing the air velocity, the reverse segregation converts to normal segregation and mixing. Then we got the segregation efficiency using this equation. This is the segregation efficiency as a function of the air velocity. The minus values show the reverse segregation, and the plus values show normal. The results are reverse, normal, and mixing. And here is a conversion from the reverse to normal. This is a result of mixture B. The conversion occurred here. Then we had the question, why does the conversion occur at this air velocity? These are pressure drop as a function of air velocity, and the dotted lines show UMF. There are 2 points. UMF of lighter particles glass beads is less than that of heavier particles, iron powder, and stainless. And the UMF of UMF with vibration is less than that without vibration. Okay. Here we add the UMF to the results. As you see, reverse segregation converts to normal near at the UMF of lighter particles ZB with vibration. This is a result of a mixture B. Again, reverse segregation converts to normal near at the UMF of lighter particles GB with vibration. they proposed the possible mechanism of reverse segregation. I'm so sorry, it's not easy for me to make the animation, so just only sentences here, sorry. They say that the vertical vibration without fluidization induces cyclic compaction and decompaction of a powder bed with an oscillating airflow in the powder bed. Air drag is generated due to the pumping of air in combination with the cyclic compaction and decompaction. Difference in acceleration from the air drag causes the heavier particles move to upward, resulting in reverse segregation. Then we considered the possible mechanism of the conversion from reverse to normal. If the air velocity, if air is vertically injected into the vibrated powder bed and the velocity reaches UMF of lighter particles with vibration, the lighter particles begin to be fluidized. The air pumping effect is weakened and difference in acceleration from the air drag becomes negligible. As a result, the reverse segregation does not occur. Above the UMF, the heavier particles sink in the fluidized bed of the lighter particles based on density difference, resulting in normal segregation. Right, next is the effect of vibration intensity on density segregation in a vibrated powder bed. George, time is okay?
Yeah, you'll finish up in 5 minutes or so. Yeah.
Okay. So quickly.
Yeah.
This is the result, last results. Then we had the question, what happens if vibration intensity is changed without airflow at the air velocity is 0? I mean the vibrated powder bed, not fluidized bed. It was reported that not only the reverse segregation, but sandwich segregation also occurred in the vibrated powder bed. Larger density particles are sandwiched between upper and lower smaller density particles. They also show the map, frequency, and vibration intensity. They use a mixture of glass beads and the bronze spheres of these size. A and C at lower frequency are reverse segregation. D at higher frequency is sandwich. E, F, and Z are both. So we also change vibration intensity and frequency to investigate this map. We use the mixture of these powders and we change the vibration intensity like this. And we follow the same experiments. These are the results. Mixing at 1.7, reverse at 2.44, a sandwich here. And reverse, partially sandwich, and reverse. Sorry, it's quick. I talk quickly. Sorry. And then we investigate the time dependence for this. 1 minute, still mixing. Then we glass beads layer appeared at lower parts. And the glass beads power layer also appears at upper parts. And finally, 10 minutes. So sorry, it takes time so quickly. Before the experiments, we expected the simultaneous appearance of a glass beads layers, but that's not true. Lower layers appears at first and upper layers appears later. This is a segregation efficiency function of vibration intensity. It looks no correlation. Then we plotted the data as a frequency versus the vibration intensity. Surprisingly, plots of sandwich are concentrated here. This is a map they shown, and this is our result. So our result indicates that sandwich segregation can occur at lower vibration intensity and frequency. All right, let me skip the possible mechanism. Anyway, sandwich segregation also occurs at a lower frequency in our study. Just finally, so let me show you. We investigated the dependence of initial state for the case of D. If the initial state is mixing, after 10 minutes, as shown, reverse occurs. But if the initial state is normal, I mean heavier particles are at lower half, after 10 minutes, sandwich. We thought the time is too short, so extended to 60 minutes, still sandwich. So mixing converts to reverse, but normal converts not to reverse, but to sandwich. Why? Right, anyway, as a conclusion, density segregation in the vibrated fluidized bed can be used for dry separation. However, the density segregation is still mysterious and complicated to understand. All right, that's it. Thank you for your attention.
Thank you so much, Jun. Really nice talk. Very interesting. And you really put a big effort in, a lot of video animation and such like that. It's much appreciated. So we have some time for some questions, and I'm sure Kevin and Dusan and perhaps others have questions. So Kevin, do you want to?
Well, thank you very much. Really appreciate your presentation. Everybody was listening to every single word with fascination.
Sorry?
Everybody was hanging off every word you were saying with fascination.
Thank you so much. Thank you so much.
I assume you're aware of all the work that was done on liquid fluidized beds in the 1980s with inversion in a fluidized bed, and where you have at low fluidization rates, you can have very fine, dense particles sitting below large, low-density particles. Have you looked for some analogy with respect to that earlier work?
Sorry, you're talking about the wet fluidized bed.
Yeah, so there was a whole debate about the whole Archimedes issue in relation to fluidized beds around 1986 in particular, Moritomi and Clift, and you could get inversion to occur. So you start off with the fine dense particles at the bottom, you increase the fluidization rate, and the fine dense particles end up on the top, which is really important in density-based separation technology. Right?
Yes.
So I'm wondering if you're aware of the water-based work that was done then, because it looks like there's some similar issues to do with the composition. We looked at the concept of a pressure gradient. Where the pressure gradient, your dense particles might interpret the pressure gradient in terms of a lower volume fraction, whereas your lower density particles, if there's a particular pressure gradient formed by high density particles, might interpret that as a different volume fraction. So in other words, high density and low density particles interpret pressure gradients differently.
Yeah.
Anyway, so a couple of questions there. One, are you aware of the water-based work back then?
Sorry, I'm not easy to understand. You're asking. I know you were talking about the wet fluidized bed or something,
yes.
and combination of the lighter and heavier particles. So you're talking about the density segregation in a
water fluidized bed. Yep. I suppose in wet fluidization, they're probably reasonably famous papers.
Yeah, I know.
Yeah, Moritomi et al. And there's a whole big debate about buoyancy forces in fluidized beds in the water systems. So I have a sense that there's some similarities between what you're doing in the dry state with what.
So you're asking me the difference between the water fluidization and the gas fluidization?
Have you looked at the water problem?
No. I'm sorry. I never done the water liquid fluidization. Just only dry one.
Sure. But I guess the question was, if you had looked at the literature, might there be some analogies, similarities? Yeah.
Sorry, I'm not. I cannot say about the liquid fluidization, so I'm not familiar. But the analogy with the dry separation like this, and now I shown the.
That's all right. No, someone else should ask a question.
Okay, so.
Simon, you have a question? A comment?
Oh, it's not so much a question, but just two comments. One is, I think for everyone watching, I think you did an extraordinary job at communicating complicated phenomena by using very good coloring and diagrams and layering of your presentation. So just to all the students out there, it was an excellent example of how you can use successive layering in presentations to communicate complicated things. And the other thing I thought was really interesting is it's also a great example of something that you think is a very simple, well understood phenomena, but when you dive down, there's still so much complexity there. And so again, I guess an encouragement to all the students that ask those questions and dig deep, because even if the field you're working in apparently is well established and well known, there's often still a lot of unknown, very interesting phenomena going on. So thank you very much, Professor Oshitani, for a very interesting talk and for raising lots of questions from what you did. So it's very interesting. So thank you very much.
Thank you so much.
Yeah.
Actually, I'm an engineer, so I'm just a separation guy. But I really enjoy the physics, quantum physics. So I'm very happy to hear that. Thank you so much, Simon.
Yeah, and I agree. Jun and his team have done some fantastic, very precise and very detailed experimental investigation, which without that level of detail and precision, you might not have seen a lot of these phenomenon, which is what Simon's saying. You think it's very simple to begin with, but there's so much complexity in there, which leads to these very interesting questions.
It was also a great example there of the plot. You had a plot where you had some data that showed a nice trend line, but when you zoomed in, there was actually this big deviation from the trend line. So it shows you also again that you can get, nature is not always a straight line phenomena. Sometimes there are weird and wonderful deviations. So I thought that, and it was to do with a phase change. It was all happening around UMF. And so I guess, again, it shows you look closely when there's a system phase change.
You are talking about this one or another one?
Yes.
You're talking
Yes,
Simon.
this one. I think this one. Yeah.
Okay. Yeah. So when there's a phase change, very intriguing, very interesting. Yeah.
Thank you.
I have a question. Your vibration intensity parameter.
Yeah.
Is that your idea, or is that come from somewhere else? Because Dusan, who works with me, has been adopting that parameter recently.
I think it's original. I mean, we decided actually the mineral sand we couldn't separate because I decided to use a very large intensity like a 6.0, 5.0, nothing. So I decided to reduce the intensity. Then luckily separated. It's our history. So actually, I didn't read the paper. Just I decided with my students.
Yep.
That's okay.
What's the particle size in that slide?
This particle size is this size, around 100.
Right. Yeah. 63 to 125.
Yeah.
Yeah. Dusan, do you have a question?
I can come up with one.
Yeah. Hey,
So
you guys
thank
go
you.
ahead.
Yeah.
I need to go to lecture.
Sure.
So,
Okay.
but I've made Leshen the host. So if I drop out,
Yeah.
you can continue discussion. So please do. And so let's all thank Jun and much appreciated, Jun, and look forward to seeing you in Australia sometime next year.
Yes, please.
And I'm afraid I've got to go to lecture, but continue discussion for a few more minutes if you have time.
Actually, I also have a meeting, so just a few minutes, sorry.
No, that's good. That's fine.
Okay.
But if you have one quick question, do send, because
Yeah,
Yeah.
just a quick one.
Yeah.
Well, thanks, George, as well for organising. Yeah, thank you, Jun, for a wonderful presentation. Yeah, just a quick one. Have you considered, or do you think you will be considering different modes of vibration? So not just vertical.
Different what? Different?
Mode.
Mode.
Yeah, so not just vertical, but
the different phase shifts and things.
Okay, we just in our device, we can just only change the amplitude and the frequency.
Mhm.
So mode. What do you mean mode? I know the surface vibration. There are many shape, but what do you think of the mode?
No, just so rather than just vertical or only vertical, having vertical and horizontal or just horizontal vibration.
We also did the horizontal vibration.
Okay.
When almost same separation efficiency, but vertical is a little bit better.
Okay. Yeah, I ask because we've been working on a device that uses a combination of vertical and horizontal vibration in addition to fluidization, and seeing some increased, not increased complexities, but some different perhaps complexities that or additional complexities to what you have been presenting, and mysteries. So but thank you. It's I did become familiar with some of your work in doing a bit of an overview of this kind of field. So it's very good for me to get this information from you firsthand. So thank you.
Yeah. So Dusan, I think we've got a few more papers to cite.
Yes. Okay.
Yeah. Thank you.
Thank you.
All right. I think we are short of time, so yeah, if everybody can sort of join in thanking Jun for a wonderful presentation. Thank you.
Thank you so much.